Okay, thank you for coming. My name is Kary Rogers, the Director of Staff Engineering at Riverbed Tech Support. That group is backline support. We handle hard problems. We interface with our development engineering team, opening bugs. We're helping the frontline TAC support. I came up through TAC, helping customers solve problems, looking at packets. And Riverbed TAC is where I learned these skills. Now I manage a team. I started a little website called Packet Bomb because I didn't want to let everything just float away into nothing. So I was at least trying to drain some of the packet knowledge that I'd gathered over the years into tutorials and whatnot. So what we're going to talk about today, I think that's all the housekeeping. We're talking about, I would call this a one-fin class. This is basic TCP throughput stuff. So we talk about TCP windows, there's receive windows and send windows and lots of windows. So we're going to talk about all those things to try to understand what are the factors that affect throughput. So if you were in my talk yesterday, this will be a rerun, but I wanted to touch on some basic TCP concepts here. I don't know how to play it. How do I play it? Like that. All right, that's my daughter. She's now, what's that?
Is that you?
And that was me in a clown outfit. The first time I tried to shoot it, I messed up and did it like later in the day. I went and did all the makeup and got dressed, got her set up, the backdrop, and then she was not having it. So didn't get anything useful. Had to wait until like the next 2 days later when I could do it like earlier in the day, and then we shot it. She's still scared of any horns that that she hears.
Clowns.
Right? No, she hates clowns. Okay, so let's talk about the basic agenda here. First thing we're going to touch on is TCP ownership. Why do we care? Who owns TCP? Let's talk about a few terms so we make sure we know what we're talking about in terms of bandwidth and throughput and whatnot. Receive side factors we'll touch on, the sender side factors, a handful of other things, miscellaneous. And at the end, I'll give you really a checklist. If you're trying to understand what the problem is with throughput, here's like a checklist you can go down and things you can check. So, at any time you have questions, just holler out, let me know, and we'll address it. So TCP, who owns it? Why do we care? If you're a network engineer, you're responsible for the network, you probably get, people blaming the network all the time, right? Is it the application? Is it the network? So people will come to you to fix the problem. And maybe this is a bad analogy, I don't know, but, if you're a plumber and you're responsible for the pipes, making sure there's no leaks, making sure that the water's flowing through the pipes and the infrastructure, no, you're not really responsible necessarily for the quality of the water. That's really not what you're there for. So they should call the county or whoever the water supply people are if they're concerned about that, but not you. You've got, you're concerned about IP and routing, making sure packets are getting from point A to point B. Maybe the configuration that everything's cabled correctly. Layer 3 and down. You've got server folks, application folks, security folks who are really kind of handling layer 5, the security stuff and up to the application, making sure that the server's configured properly, that it is, at least connected to the network and can talk on the network. But TCP is, it lives on the hosts that are talking. So who owns that? And that's the problem, is it sort of gets left behind. There's fighting, squabbling over, pointing fingers at the problem, and if it's a TCP problem, it's probably up to you to just go ahead and figure it out. And the sooner you can figure it out and say it's, you know, your server, your application, something else, the sooner you can go back to surfing Reddit or whatever it is you might do. So, bandwidth. I looked this up on some dictionary website. It says it's a measurement of the ability of an electronic communications device or system, such as a computer network, to send and receive information. So when we talk about bandwidth, we're talking about you have maybe 100 megabits, a gig, 10 gig. That is the capacity of the system in which two hosts are talking, right? So that's the theoretical capacity, what you're trying to get to. You're not going to get maybe the full amount due to overhead and whatnot, but that's what you're shooting for, is to make full use of the bandwidth that is available. But when we're talking about throughput, that's what you're actually getting within that system. If you have 100 megabits and you're getting 20 megabits, well, that's 20 megabits of throughput in the system that is theoretically capable of 100 megabits. You know, that's the question a lot of times is, I'm paying for this much bandwidth and I'm only getting this. Is it a capacity problem? Is it something else? So we're going to work through that so you can maybe help yourself to figure out what's going on. So what's the difference? Bandwidth, total raw capacity, and throughput is what you're actually getting within that system. So what we're going to focus on today, a single connection between two hosts, right? So we're doing FTP, you're pushing, you're getting. HTTP, you're doing a get, you're downloading something. Bulk data transfer, how to make it go as fast as possible. And when you're not getting what you think you should get, how do we figure it out? So BDP, you've probably heard this around while you've been here. What is BDP? What does that stand for? Bandwidth delay product. So we're talking about the amount of data TCP should have within that pipe, the transmission path, at any one time in order to fully utilize that capacity. So bandwidth, 100 megabits, whatever, times latency, 20 milliseconds. You can divide that by 8 to get the bytes. That's how many bytes it takes to end-to-end fill the pipe. I like to think about, for me, like golf balls in a PVC pipe. How many golf balls does it take to fill a PVC pipe? If you have a short PVC pipe, maybe you fit one golf ball in. That's a one golf ball BDP, right? If you make the PVC pipe longer, maybe you can get 6 golf balls in. So now you have 6 BDP pipe for golf balls. If you make it bigger round, bigger diameter, maybe you can fit 3 golf balls in at any one time. And with 6, so 3 go in at once, you can fill it with the length of 6. That's what? 18 BDP for golf balls, right? I don't really play golf. I'm really bad at it. So this is a question I'm going to be asking you throughout. Based on the factors that we discuss, we're going to keep adding more and more, I'll say complexity, but more factors for you to consider. The question is, I have data to send. I want to send all the data. But what are the factors that will limit, or that I should take into consideration about how much data I can send in one go? So what we've learned so far, only thing we've covered is BDP. To fill a pipe, I can send BDP bytes between two hosts to reach what we're trying to get in terms of throughput. So throughout this, we'll use a little setup. Imagine there's a zip file of cat pictures. Everyone has these, right? On your computer. You get bored at work, you look at cat pictures. Imagine there's a zip file. It's 256 kilobytes. And so that is sitting on a drive, and you want to send it via FTP or whatever. The application is going to start reading that file, and that is a stream of data that it's going to send across the network. So this represents the stream of data of all the cats.zip. 256K ... is data we have not sent yet. So we're going to be using this framework. So the factors that we're going to discuss today. pretty simple. The amount of data the receiver says it can receive, and the amount of data the sender thinks it can send. I mean, that's pretty straightforward. So let's talk about the receiver first. You hear about receive window, TCP window when we're looking at packets, because there is a window in the packet. It's the receive window. RWIND, socket, receive, buffer. These are all the same thing. They all refer to the same thing. It's the amount of space that an application allocates to receive data from the other side. So it's a socket buffer. If you were in Hansong's talk yesterday, he talked about this quite a bit. You create a socket. I want to talk to this IP address, this port, and I'm going to allocate some space to receive data from the other host. It might be a system default. It might be that the application requests a specific amount. The application then reads the data from that buffer to free the space up from the buffer. And this is, as I said, advertised in every packet in the TCP header. Whether you're sending or receiving, remember this is duplex, right? You've got a stream going in each direction, and there's a receive window on each side. So this is just from the perspective of receiving. If I'm an FTP server and I'm always sending data, well, my receive window doesn't really matter much. It's the receiver who's taking in the data where it matters. So window size value, it's right there in the payload, in the TCP header. You can see it. It's 16 bits. That's 64K max. Back in the day, 64K was plenty, right? The BDP for connections between two hosts might have been plenty. But today, it's not. You cannot fill the pipe. You might have a BDP of much higher than 64K. So if your receive window is limited, you'll never be able to fill the pipe. So we have window scaling, which allows up to 1 gig, RFC 1323. It must be supported by both hosts to be used. And the way you determine that is in the three-way handshake. So when you're gathering data, when you're reproducing a problem, capturing the data, make sure you start your capture before you do the test, because you want to get the beginning of the connection. In the TCP options, you'll have the window scale, which is just a bit shift, right? We have 16 bits that we can use, and this tells you how many bits to just shift the value over by, which means you're multiplying by a value. So if it's 8, you multiply it by 256. Now let me go back to the previous one. So you can see the value advertised in the packet is just 3045. But because we have a window scale factor of 8, we multiply that value by 256, and we get the actual calculated window size, 700 and something K, right? Anything in Wireshark that has square brackets doesn't exist in the packet. It's calculated for you. It's handy information for you. But it's not in the packet itself. How are we doing so far? Good? Okay, so that is the receive window. Now, we have 256K of cat pictures, and our receive window is 64K. So at this point, if I'm the sender, what's the most amount I can send in one go? The minimum of the receive window or the BDP, right? If my BDP is 100K and my receive window is 64K, well, I can't send 100K. I'll overrun the receiver. Let's have a look at this in Wireshark. Where is Wireshark? There's Wireshark. Is this somewhat readable? Make it a little... Okay. So we have a capture. We have the three-way handshake. We're going to have a look and see what's being advertised in the options. MSS. Window scale is 0, so whatever's advertised is what is used. Same for the other side as well. We have a round trip time of just under 100 milliseconds. So the delay between the send and the SYNAC, this was captured on the client side, is around 100 milliseconds. So the tool that I like to use, once I've done a little bit, kind of get the lay of the land, what are we dealing with here? The tool that I like to use is the stream graph, TCP trace. And all this is sequence number over time. Sequence number is just bytes. When we're transferring data, we're transferring a byte stream. We have TCP is what reliable, blah, 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 How we keep track of where we are in the byte stream, if we need to retransmit or if something's out of order, is with the sequence number. And it's just representing bytes. So with relative sequence number, it starts at 0. That's a setting in Wireshark. So at the beginning of a stream, it will be set to 0. So we have sequence number, again, which is just bytes over time. Bytes over time is throughput, right? So we have a slope. The steeper the slope, the more data we're transferring in the smaller amount of time. It's higher throughput. The flatter the slope, the slower the throughput. So that's what we're looking at with this graph. And we can zoom in, and I'll give you what's going on with these things. So these are the packets, individual packets being sent. Packet train, out the door. Those are packets. The bottom line are acknowledgments coming in. And the top line is the receive window. So you've got 3 bits of information, packets going out, the acknowledgments coming in, and the receive window that's being advertised by the receiver. Now this is a stream graph, right? So you have to click on a packet that is from the sender to make this. If I were to click on the client who's receiving the data and try to generate this graph, there's nothing there because it's not sending any data. Other than the initial GET request, there's nothing here useful. So if you open this graph and it looks like this, just switch the direction. So let's go down here to the beginning of the capture. We see data being sent a little bit at a time. TCP slow start, right? And then we get to a point where we're sending out a bunch of data, and then we're not doing anything, right? So this top line, again, is the receive window. So what this is showing us is that we sent out this packet train, and then we stopped once we hit the receive window. We can't send any more. When the packets touch or get very close to the receive window, we have filled the window, and we can no longer send data. So we have to wait. Remember, there's a round trip time of 90-something milliseconds. So anything that's flat and there's no movement is just time wasted. So this flat line here is just we're waiting for something to happen. And as these stair steps go up, these are acknowledgments coming in. So we sent as much data as we could. We filled the receiver's window, and we have to stop. We're bound by the receive window. We wait for acknowledgments to come in. As they come in, that frees up some space. And you can see we're sending a couple of packets. An acknowledgement comes in. TCP generally acts every other packet. So one acknowledgement is acknowledging 2 packets. So I get an ACK in, I can send 2 more. Yay, send 2. Wait for another ACK. Send 2 more. And this behavior continues until we've sent the entire amount of data that we're sending in this go-around. Once we've done that, we wait. All the rest of the acknowledgments come in. All the outstanding data is acknowledged. We send another packet train. And this continues over and over and over again. So the low receive window is slowing us down quite a bit. And you can see this in the capture. If we come down, let me add, we're going to talk about bytes in full. Well, we'll do that later, actually. So we can see the receive window. This is data coming. This is data being sent. Data being sent. And look, we send a packet. We send a packet. We fill the window. We have to wait for this acknowledgement to come in. We send a packet. We send a packet. Wait for the ACK to come in. So that's the receive window. Yeah, let me add. All right. And the window, do I have window size here? Yeah. So the window, yeah, is 64K. So we can send up to 64K, then we have to stop. All right. So the receiver side, pretty straightforward. The other part of the other scenario, which that doesn't show, this one is we fill the window, we've sent the packets out the door, we have to wait, and the acknowledgments come in, but the receive window is always 64K. That means the application is continuing clearing out the buffer. But if you see the receive window from the receiver decrease over time, maybe all the way down to 0 or some other number, that means the application's not taking data out of the receive buffer fast enough, and it's filling up. That's the other scenario that you can see. So, now then, the sender. We're talking about a couple of topics here. Bytes in flight is really more of just a concept that ties into the other issues of congestion window and send buffer. So bytes in flight, this is sort of the flip side of the coin of the receive window. I know the receive window is 64K. I know there's a latency of almost 100 milliseconds. So I know that I can send 64K, and that's all I can do. So that is data that has been sent but not yet acknowledged, meaning the data has to go all the way across to the receiver. The receiver has to get it and then send acknowledgments back. One full round trip. The data that's in flight that is not acknowledged, well, bytes in flight, right? So what that looks like is, let's say we're going to send 64K to fill the receive window. Maybe we've sent up to 48K so far. There's still 16K of usable window that we can continue to use. And let's go back to the PCAP that we were looking at, and I'll add bytes in flight. Bytes in flight is a good thing to have when you are troubleshooting throughput. Okay, so let's start at the beginning of a packet train. So here's a bunch of ACKs coming in. These are from the receiver, TCP link 0. They're just ACKs, win size 64K. And we have data. TCP, we're sending 1460 bytes. The bytes in flight is 1460. That means we have one packet in flight. All the outstanding data has been acknowledged. There's nothing in flight. We're all caught up. Here comes a new packet train. And remember, it has to travel for 50 milliseconds, half of the round trip, to get over there. And we can crank out a lot of data in 50 milliseconds. So you can see with every packet being sent, the bytes in flight, meaning data that is not yet acknowledged, continues to go up. Continues to go up until we fill the window. We have to stop. At that point, we have to wait a full round trip. Here's the delta column. 100 milliseconds passes. So we just very quickly send out all this data, 64K worth. And we have to wait a full round trip for those ACKs to start coming back. And as they come in, remember, one ACK frees up 2 slots. We can send 2 more. So we go data, data. Oh, window's full again. So you can see that the bytes in flight drops by 2 MSS size. And we can send 2 more. And then it goes back to full. And this repeats over and over again until the packet train that we wanted to send is done. And then we have to wait for all the acknowledgments to come in. And bytes in flight start over. All right, that's bytes in flight. Any questions so far? Great.
The bytes in flight maximum is buffer size?
The bytes in flight depend on the factors that we're talking about now. So it could be bytes in flight will be the buffer size, which is what we just saw. It's never going to go more than the receive window. Can't. That's breaking the rules. Because if I send one more than 64K, that may get dropped. Maybe not. Maybe the application's clearing out fast enough. But the rules of TCP say I've sent out the door 64K of data, and I know that your receive window is 64K, I have to stop until you tell me that you got the data. So we'll see that there are other factors that come into play that will limit bytes in flight. So for long fat networks, we want the bytes in flight to go up and up and up and up and up and up and up towards BDP. So CWND, congestion window. You've probably heard this, seen this. This is where the receive window is the flow control of the receiver saying, give me more data, nope, stop, give me more data, stop. Congestion window is the sender side flow control. It's based on the capacity of the network and the conditions of the network. You cannot find this in the header. You can go look in the packet, you're not going to find it. This is a variable, a state variable in memory per connection. So you can infer what it might be by looking at the PCAP and how much data is sent in one go-around, but there's no way to definitively check in the packet capture. We refer to it in multiples of MSS. So we know our MSS for this is 1460. So if I'm sending 2 packets, I have a congestion window of 2. If I send 4, I have a congestion window of 4. So it's in multiples of MSS. Generally, it starts small, something like 2 or 4. More recently, we're starting to see things like 10. The amount of data that you can send in one go at the beginning of a connection. Where this really matters is short-lived connections, especially HTTP, or I've seen it be problems with batch file transfers for small files, because we don't ever by the time you ramp up, it's done. So if you start with 1, 2, 4, but if you start with 10, you're going to ramp up much quicker, increase performance. So it increases exponentially during the slow start phase of the connection. So if I send 1, I have to wait for acknowledgement. Now I can send 2, wait for the acknowledgements to come back. I can send 4, and it continues doubling like that pattern, like an exponential curve going up until it reaches a threshold. The threshold isn't set by the operating system. It's probably configurable, but it is, again, not something that's visible to you looking at a PCAP. It's, again, a state, a variable, a setting, registry, whatever, on the operating system, such that it will grow in an exponential fashion until the congestion window reaches a threshold, and then it changes to linear. And I'll show you what that looks like. It will continue, the congestion window will continue to grow until it either hits the receive window. The receive window is 64K like our example. It can't send more than 64K worth of packets before it has to stop. Congestion window has to stop. Or there's packet loss and we have to go into recovery. And how it does that, well, it depends. So this is a graphic I stole off the internet somewhere. It's very generic, right? You may not see this exact pattern. This is this is generic. Each dot represents the congestion window. So we start at 1, then we go to 2, then we go to 4, and then at 8 is our slow start threshold. From there it switches and goes linear to 9, 10, 11, 12. And it will continue growing that way until the receive window is hit or a packet is lost. We have maybe a timeout. So every bit of data that I send, I'm setting aside and setting a timer. And if I don't get it acknowledged before the timer goes off, I've got to resend it. When I do, with a timeout, I might go back to slow start like this. And it will also adjust the slow start threshold. How that works, how far do I back off, how is the threshold reset in packet loss, completely depends on the algorithm, the TCP algorithm that's being used by the host. It's different for Windows, Linux, etc. So, as I've said, the sender is bound by the congestion window even if we have space with the receive window. The receive window is 64K. We're at the beginning of a connection. We've got up to a congestion window of, say, 10 packets. Well, we're going to stop, and we're going to wait for acknowledgments to come in. As I mentioned, it depends on the algorithm. Back last summer when I was looking, I was trying to figure out what some typical settings were. So This is not the gospel truth. You know, you can look online to see what maybe things have changed. But New Reno, what I found was what is used by Windows clients, DC TCP or C TCP for Windows servers, Linux, Cubic. There's other ones, Reno, New Reno, Vegas, lots of cities in the Southwest where you can lose your money. Somehow it's tied to TCP. Now, if you do want to find out what it is, I've seen a couple of tools. There's probably a bunch of other tools that I just don't know about. But the one that I've used is called TCP Analyzer on Windows. It's part of a package that you download. You can Google it, you'll find it, install it. It's kind of like a graphical netstat, and then you get a bunch of state variables about the TCP connection. And then SS on Linux, socket statistics, I think maybe -E or something will give you a readout of the RTO, the retransmission timeout setting currently, the congestion window and whatnot. Does anyone know of any other tools that they've used to see this, like TCP state variables? Well, if you find one, let us know. So now, back to our cat pictures. So we've sent a chunk of data. The ones that are a solid line, sent, acknowledged, done. Our sliding window is moving, right? We've got this stream of data. We have our sliding window of data we're sending and it being acknowledged. 64K send window. But currently, right now, our congestion window is at 33. That times MSS is 48K. So that's where we are in the current state of things. So we're not going to send more than 48K before waiting for acknowledgments. So now, one more variable to add to our little thing here. How much data can we send in one go? The minimum of congestion window, receive window, and BDP. So let's have a look at the congestion window. I'm going to switch to this. Back to our favorite tool, TCP trace. Let's zoom in. So, the beginning of the connection, we send a packet. We wait full round trip time. So our congestion window is at 1. That one gets acknowledged. You can see that the green line goes up to acknowledge it, and then we send some more. It's not always super clean, like 1, 2, 4, 8, 16. Sometimes it is, sometimes it isn't. But you can see pretty clearly the general pattern. Here, we're up to 4 after the round trip time. Now we're at 8, 16, 32. So that is the congestion window opening up at the beginning of your connection during TCP slow start. And you can see we're nowhere near the receive window, so we're not bound. The receive window is way up here. We're nowhere close to it. So we're not bound by the receiver. We are bound by the congestion window.
Did it always start with 2 or?
No, it depends. 1, 2, 4. Again, some things. I think Google likes 10. So I'm not sure if Chrome is using 10 these days. But there's been a lot of talk like CDNs. There's a web page, you can Google it, for initial congestion window, like init CWND. And there's a report where they've done a scan of a bunch of different providers, CDNs, etc., applications, and what they use. So it can be 1, 2. Some of them are using like 40, which is probably, that can cause problems. Because the idea of slow start is to play nice, right? Let's probe the network to find what we want. And if we're just starting out with like 40 or 50, as long as the network's not collapsing under that, it's a good experience for the user because we're sending a lot of data right off the bat.
The receiver usually they wait for the 2 full MSS before send that.
Yes, two packets. I think the RFC says like that should language 2 full MSS worth to send an ACK, but some operating systems will just get 2 packets and ACK Other ones will wait for 2 full MSS. But the general pattern is data, data, ACK, data, data, ACK.
In this case, the sender minimum should send at least 2 in the condition. Otherwise, you don't get any response.
I see what you're saying. So yeah, if you send 1, it may wait before it may be waiting for that second one. Linux has a mode called Quick ACK mode that it uses at the beginning of a connection for that reason. So in the beginning of a connection, Linux will ACK every packet up until a certain point, then it switches back to every other. Okay, next factor, what we just talked about, congestion window. The next factor is the send buffer. We've already talked about the receive buffer. We ask the operating system for a socket. We ask for a buffer to receive data into, but we're also allocating a buffer to send data to the other side. The application is reading the cat pictures off the disk, and then it's giving it to TCP into the send buffer for TCP to send it. Again, this is either an OS default or it's set by the application. The optimal size of this, as with the receive buffer, depends on the BDP, depends on what we're trying to do. Lots of operating systems these days kind of do it on the fly, and it's adjustable. Auto-sensing, the network. The issue is that I'm just going to bring up this little link. When I was researching this a couple of years ago for someone who was seeing a send buffer issue or a performance issue, let's see if I found this article on Windows Dev Center. It talks about socket options and whatnot, and down in the remarks section, it talks about the ISB, the ideal send backlog. All that means is the amount of data you have ready to go to send onto the wire. The send buffer size is what that is referring to. And it says here, yes, this page is very helpful. I'm not going to click that. It's important to keep a sufficient amount of data outstanding, sent but not acknowledged, in TCP in order to achieve the highest throughput. So this value depends on this ideal size, which is a function of the bandwidth delay product of the connection. So if I have a BDP of 100K, that's how many bytes it takes to fill the pipe, and I allocate a 32K send buffer, I'll never be able to fill the pipe because I can send 32K out of that buffer before I have to wait for it to be acknowledged. So, back to our cat pictures. We have some data sent and acknowledged. Our window's sliding forward. We have a 64K receive window. We currently have a congestion window that is opened up to 48K. But the application that's doing the sending has allocated a 32K send buffer. So, now, how much data can we send in one go per round trip? At this current time, well, it's going to be the minimum of the send buffer, the congestion window, the receive window, or the BDP. Let's have a look at that. So here we are back at the same PCAP. We saw the slow start. It was essentially doubling every round trip. And then it hits a point where it's sending a chunk of data just all in one go. And then it stops. Right? So maybe that's where our congestion window is. It's opened up to this point, and that's all we're going to send. Okay, fine. You can see the stair steps going up, 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 and meaning it has now acknowledged all of this data. So at that point, we should increase the congestion window again, right? So we should see a longer packet train. Depending on what mode we're in, if we're still in slow start, it should be quite a bit bigger. If we're in linear growth, it'll be a little bit bigger. but we should still see some growth. And I don't know, it looks kind of the same to me. We wait for all of that data to be acknowledged. Again, we have a send buffer size. We sent all of our data. We're waiting for it to be acknowledged, and we send another chunk of data. And you see this happening over and over and over again. A couple of weird ones where it sends half, then half, with a small break. But for the most part, a chunk of data, we wait. A chunk of data, and it doesn't really seem to be growing. And if you look at the captures themselves, let's come down. So here we go, the start of a packet train. We have bytes in flight 1460, right? So that's the engine on the packet train heading out. We're sending data. This is a push bit, meaning that's the end of a chunk of data. What do you notice about the point where the push bit is? Anybody? I think I heard it. Push bit came in exactly 64K. When you see numbers like that and something correlating it like a push bit, that should be a flag, something in the back of your head as a packet analyzer person, an analyst. That's probably better. That should be a flag. We had a push bit on exactly 64K. Okay, let's keep going. Our bytes in flight continue to go up, so this is the packet train going out. And we have another push bit. And what do you notice about that? 128. So we have probably two writes going into a buffer, two 64K writes going into a buffer, probably 128K. And at that point, we stop, go over to our delta, there's your 97 milliseconds. So we send 128K, and we stop. And we wait for all the acknowledgments to come in. So that's 100 milliseconds per chunk of data, and we start over again. And so this pattern repeats itself over and over and over through the after slow start, with some just slight little variations in the exact amount of data, but it's all pretty much the same. 64K, 128K, wait. It never grows beyond that. There's no packet loss. We can look in here and see there's no packet loss. There's nothing that we can see in the behavior to limit the growth of the congestion window, if that's what we think the problem is. And because we see these patterns that are very striking of exactly 64K and 128K boundary on the push bit, we can conclude very reasonably that this is a send buffer problem in the application. In this particular case, I believe it was a Tomcat server. You're downloading files from Tomcat, and sure enough, if you go into the settings and change the send buffer size, poof, fixed. It will fill the window and drastically increase your performance.
So, question, sorry, why didn't it start sending stuff as soon as it started receiving some of the apps?
That's a good question. That's different from the one we saw before. In this particular case, it seemed to be something.
Is that something that on the Tomcat that would have had the configure to not do?
I believe it's a Windows. Let's just call it quirk, maybe a bug. Maybe the way that it handles in-memory and data and passes it back and forth between the kernel and the user space.
Right.
I don't have it linked because we weren't really going to go into the details of this. But actually, I have a case study on my website. If you go Packet Bomb, case studies, look for slow Tomcat. That's what this one's from. And at the end of it, I link a Microsoft article, a different one, that specifically has, I think it's like a bug. And it's like if you have this data pattern,
yep,
which is what we have, there's it hangs, it's like a, what do you call it, a lock? Deadlock.
Right, okay.
So that's like the other one we saw. As soon as the ACK started coming in, I can send a little more, I can send a little more, I can send a little more. In this case, it didn't, and it seemed to be a Windows quirk.
Okay, all right. So where the stack was handing onto the application.
Yeah. It's the type of I/O it's doing, and following on these data boundaries. I'm not a Windows or low-level guy really, but
But again, the objective was to determine it's not the network. It's
right. I mean, absolutely, this issue is the SYN buffer issue on the application, but it was made worse by this weird Microsoft issue. Because I could do this, I could stand up a Tomcat server on Linux, and it wouldn't have that problem. It would stop sending data, but it would send it out a little bit at a time, which is still not great. Okay, so how are we doing? I think we're moving through this pretty good. We'll go to when? 3:15? No, 3:15? Yeah, we got plenty of time. Checklist. So I would say, people contact me about performance issues. It's not always, one connection, a throughput, bulk data transfer. It is a lot of times. It may be other things. But when you're looking at bulk data transfer, downloads, uploads, etc., between two hosts, this checklist and things we've talked about will cover the majority of them. There are other factors, of course. We're going to touch on some of those. But if you can get through these, I think you'll uncover most of the issues. So, first thing you want to know, what's the BDP between these two hosts? Bandwidth times latency. You want to make a note of that, just so you know what you're aiming for. You have to keep in mind that between two hosts, there are a lot of buffers, a lot of devices. So you're probably going to see bytes in flight exceed the BDP. Okay. But you want to at least get to BDP. If you're not getting there, you got a problem. What is the advertised window of the receiver? So make sure you have the three-way handshake. Or if you don't, if you can find it out another way, asking a server admin to check or something, if you can find it out, your capture didn't get three-way handshake, you can manually add the scaling factor into the PCAP. But you need to know accurately what it is. So, are the bytes in flight, which is a representation of the congestion window, is it increasing with each round trip? And is it going towards BDP or the receive window? Is that happening? If it's not, does the sender stop and wait for ACKs after sending the same amount of data over and over and over, as we just saw in that capture? And I've got another one similar, that's another case study that's a slow FTP upload. Same type of issue. You see it, the receive window's up here, it sends a packet train and stops. We wait for the round trip time, then we send the exact same chunk of data, whatever it was like 16K, I think, something like that. I've seen it a lot of times. If there's packet loss, you see retransmissions, you see dupe ACKs, previous segment not captured, potentially you have packet loss, and that's going to stop the congestion window from growing. If you get through all this and you say, and it's good, then great. There may be a few other factors, but before we do that, let's have a look at what packet loss looks like in terms of performance. So, is this a big file? I can't see the bottom of my screen. There it is. Okay. So, we want to get inside LAN. All right. So we've got a couple of connections. This is HTTP. It's a get 100 meg file, just a download. So we're going to click on a data packet from the server and look at our throughput graph, TCP trace. So it's going up and to the right, yeah? But, it looks a little weird, right? It's got some little waves in it, up and down. I mean, again, the overall trend is up and to the right, but there's something going on. If we zoom in, we can see that exponential growth of slow start, going up and up and up, and then the angle of the line changes. Now maybe that's because we hit slow start threshold and it's going into linear, maybe it's something else, but anytime you see a change in angle, something happened and it's a change in throughput. If it goes a little flatter, you've lost throughput. If it gets steeper, you've gained throughput. We can zoom in and see what's happening here. And all these red lines are SAC blocks, selective acknowledgement blocks. So that tells me there was packet loss. And this is a packet right here. Remember, this graph, everything going to the right, this is your right, is later in time. And everything going up is further down the byte stream. So if you see a packet like this one that is to the right, but below something that was already sent to the left, all these packets, that's probably a retransmission. It's data that was already sent, but we're sending it later. So we have retransmission, and then we have the congestion window is lowered. You can see the amount of data that was sent in each packet train is now a good bit less. And when you zoom out, you can clearly see that change. You keep zooming out, go up, you see, all right, here we go. We're ramping back up, and there's a change again. You go in, you see SAC blocks, you see a bunch of these little retransmissions down here. These are all retransmissions, right? Because they're to the right and below all these over here. So this is packet loss. You see throughput goes up and it comes down. Throughput goes up and it comes down. That's what packet loss can look like in the TCP stream graph. Okay. So, what are we missing? What else? What else could affect our throughput when we're, again, we want data to be sending all the time. The more data you can send in one go, the more throughput you're going to get. So when we have pauses for something, we've already talked about the big ones. But I think it was mentioned earlier a little bit, especially when you send one packet. What's another delay that we might see on the receiving end? If TCP normally,
Applications not clearing the receive buffer.
what's that?
Applications not clearing the receive buffer.
It could be right. We would see the receive window go down to 0. We would see that as a function of the receive window. But if we send a packet train and we're ACKing every other packet, and there's one straggling odd numbered packet at the end, we might see a delay. What is that called? Delayed ACK. So if I'm sending a packet train and it's ACKing every other one, and there's an odd number, so there's one packet left to be acknowledged, I'm the receiver. I get it. All right, well, I'm going to wait for another one because I'm supposed to ACK every other. But when I receive it, I set a timer. And if I don't get another piece of data, another packet, when the timer goes off, okay, I will ACK now. That's a delayed ACK. A typical timer is 50 milliseconds or 200 milliseconds. I see 200 milliseconds a lot. So that happens occasionally. But when you couple that with another function on the sending side called the Nagel algorithm, which helps determine when to send data, if I have a full MSS worth of data to send, and if I don't have it, when do I send, under what conditions? We'll go into the details because this video is everything you need to know about the delayed ACK and Nagel deadlock. Let me bring it up so you can, I'll kill the volume so it doesn't blast. Let me bring it up so you can see the title of it and you can view it in your own time. Wireshark tutorial of TCP Nagel and delayed ACK interaction. It's on Hansang's YouTube channel. So if you're not all subscribed to his YouTube channel, you need to do that. So that's a video that will describe it in greater detail than I could. There was one downvote?
Yeah.
Oh, it wasn't me. Jerk. Okay, so there's a few other things. Delayed ACKs. If you see one packet being acknowledged, and there's a delay before that acknowledgement, it's a delayed ACK. Now, what if there's no unacknowledged data, but there's a delay? So if we're analyzing the TCP layer, what's happening at TCP? We've got bytes in flight, we've got ACKs coming in, and there's a delay. There's no outstanding data. All the data that's been sent has been acknowledged. What might be causing a delay there? Yes, could be. Well, we would definitely be able to see that in the ACKs coming back would have a 0 window. But if we don't see anything from a TCP perspective, we're looking at TCP, we're like, well, there's a delay here, but I don't see a TCP issue. I think you mentioned earlier, the application could be having issues. So if it's having trouble taking data out of the receive buffer, or it's off busy doing something, you ask for you see this a lot with HTTP, you see a GET request from a client, and immediately TCP on the server acts it, just a naked ACK back, saying, TCP says, I got your request, but that's just TCP data. Then there can be a 400 millisecond delay before you see the server response. Because the server had to go pull up a file, talk to a database, go do a query, do a REST API, something. That's application delay. Now, if it's bad enough, you're going to have to then dig further. What is the application doing? Does it have enough free threads, free children to talk to clients? Is there a database issue? But if there's no TCP layer issue, request comes in, TCP acknowledges it immediately, and then the next packet is a large delay, and it's a server response or something, that's an application or a server issue. Another one, user interaction. If it's Citrix, if it's even HTTP, or if you're downloading your cat pictures, you got to take time to look at the pictures. So user could be doing something. If you're testing with someone, you want to understand what they're doing. Be somewhat familiar with the application if you can when you're looking at the data to try to discern, is this user think time? Well, so that is the checklist. These slides will be available on the retrospective, so I encourage you to go and pull these down. If you come up with something that's not here, please reach out to me. I'd love to hear about it and add it to the list. But I think, in my experience, the checklist is gonna cover between the receive window and the congestion window and packet loss and send buffer. That will cover most throughput issues that I've looked at. Occasionally, you need to go a little deeper. Maybe that'll be version 2 of the presentation. So, any questions you have, you can ask me now. You can ask any other presenter. AskWireshark.org is a good spot. I'm always interested in case studies. People reach out to me all the time for help with looking at PCAPs to get feedback. Sometimes I turn them into a case study for the website. Sometimes I don't. Either, if you heard me yesterday, people tend to ghost on you. They come to you, you look at their data, you give them feedback, and you never hear from them again, and they don't respond to your request to find out what happened. It happens. So, but if I can, I create a case study out of it. So feel free to reach out to me that way. Please fill out your survey in the app. Was there any gaps here? Anything that I could cover that, again, I'm trying to keep this, beginner level TCP throughput stuff, but I'm happy to hear your feedback. You can reach out to me this way, Twitter, email, check out the case studies on the website, and give you some time back. Thanks for coming in. Appreciate it.